Not every curved pattern needs a tree model. SplineTransformer lets a linear model bend while keeping the feature effects readable. You'll understand the pattern behind a pipeline that fits curved mileage signals with splines and keeps predictions transparent. I'm Professor Pi, teaching AI foundations with simple Python. When you look at real tabular problems, many relationships are not straight lines. A feature might influence the target in a gentle curve or in a few local bends. Tree ensembles can learn those shapes, but they hide which part of the input caused the change. Splines give you another option. They let a linear model combine local smooth bumps to follow curves while keeping coefficients interpretable and stable. Imagine predicting fuel efficiency from odometer or age. Success is a model that follows the smooth decay of mileage with age, but still lets you point to the feature shapes that matter. Splines often win when you want smooth extrapolation and a simple explanation of which input ranges drive predictions. They scale well for medium-sized datasets and slot easily into scikit-learn pipelines. The intuitive idea is simple. Instead of forcing one straight slope, we build a few overlapping bump functions across the input range. Each bump only activates near its knot. A linear model learns weights on those bumps, and the weighted sum becomes a smooth curve. With few knots, you get a smooth, global shape. With more knots, you can follow tighter bends. The trade-off is familiar. Too few knots underfit, too many wiggle. We will build a short toy workflow that walks this through. First, we show how a plain linear fit misses curvature. Then we reveal the SplineTransformer basis. Next, we compare pipelines with and without splines on a holdout set. Then we sweep knot counts to pick a sensible granularity. Finally, we inspect the trained pipeline to find which spline basis actually carried the signal. That inspection is the part that makes splines useful in practice. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, show the baseline failure of a straight model on a curved signal. This snippet uses scikit-learn linear regression to show why a straight fit undershoots a smooth nonlinear pattern. Linear regression on X tries to compress the entire sine-shaped signal into one slope and intercept, so it cannot follow the bends. We generate X with np.linspace and Y with a noisy sine, so the mismatch is obvious without extra plotting. The model lin fits in one line because scikit-learn handles the closed-form solution internally. The printed baseline R2, hovering near 0, confirms the straight line fit leaves lots of curvature unexplained. Next, inspect how SplineTransformer constructs localized features so you know what the linear model will see next. This example inspects scikit-learn SplineTransformer so you can see how each sample activates only a few splines. Without this peek, it is hard to trust that the engineered features stay localized instead of smearing across the input range. We reuse X, call spline.fitTransform, and capture XT to expose the numeric basis functions that linear regression will later digest. np.countNonZero on XT40 shows only degree +1 active columns, so you grasp the localized bump each spline contributes. The printed active per row and total splines values make the localized sparsity explicit, building intuition about the upcoming linear fit. Now, compare end-to-end performance with a proper train test split to see the generalization benefit. This code trains scikit-learn pipelines with and without SplineTransformer to show the nonlinear boost on a test split. If you only look at training error, you might miss how badly the straight baseline generalizes to unseen positions. Train test split gives us xtrain and xtest, so we can evaluate both models under the same holdout. Base split uses linear regression alone, while spline model chains SplineTransformer and linear regression through make pipeline to automate the preprocessing and fit. The printed linear R2 and spline R2 show the spline-enhanced pipeline, lifting predictive power on new points. After that, we need a practical rule for picking how many knots to use, so we sweep candidates and compare. This snippet loops over SplineTransformer knot counts, so you can select a data-driven setting. Picking n knots blindly risks either underfitting with too few bumps or overfitting with wiggly artifacts. We reuse scores as a simple list, so the for loop can fit a make pipeline for each candidate. Within the loop, model.score on xtest captures validation performance without extra boilerplate, keeping the comparison aligned with snippet 3. The printed best n knots and best R2 tell you which spline granularity wins on the holdout. Finally, make the chosen model and read its coefficients so you can explain the curve in human terms. This code reveals the dominant spline feature from the final scikit-learn pipeline, so you can explain the shape it captured. Transparency is the payoff for staying in a linear family, so we should inspect coefficients instead of guessing. Final model rebuilds make pipeline with the best n from snippet 4 and trains on the full xy to use every observation. Spline step get feature names out, labels each basis bump, while linstep.coef stores the matching weights that linear regression learned. PD dataframe organizes those arrays, so IDXmax on the absolute column is an easy way to spotlight the strongest curvature cue. The printed peak feature and weight identify which spline basis drives the prediction, making the model's emphasis legible. In a real project, you would replace the signed toy signal with your actual mileage or sensor trace. Use cross-validation instead of a single split, and save the pipeline object for inspection and deployment. The same inspectable coefficients give you a human-readable story for stakeholders. Splines let a linear model add smooth, local bumps to match curves. Use them when you want smooth fits and clear feature-level explanations. Caveat: choose knot count carefully, because too many knots create wiggle that looks like signal but may be noise. Next step? Tune ncots with cross-validation to find the right balance for your data and freeze the pipeline you can explain. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.